So this is to find out whether two variables, two categorical again, okay, again categorical variables are independent or not. So how do we do this? So whether some association exists between two variables, whether they are dependent or independent, that's what it tests. So chi-square is non-parametric as usual. It doesn't take into account the parameters mu, sigma, etc. So it uses the same test statistic and it just extends that thought. It just compares two categorical variable to find whether they are independent. So what do they do is here that, so the test statistic remains same. So what do they do that? They put the two categorical variables in a tabular format. So what do they do? So they will create a table like this and they'll put all the observations here. Say for example, if I have two variables, one is x, one is y. So I'll put one towards the in the row, x will be here and y will be in the columns, okay, and we'll get a combined probability. So we'll put all the probability values here, okay, for each one of them. So this will be like xi, yj, okay, whatever is the value. And using these values, I'll put it in this table, and from all these values that I have, I'll find out whether these two are dependent or independent. Very simple test. I'll use the same statistic and I will just find out. I'll give you the details how we'll find out, but this is broadly the thing. I'll put all these values and then don't you see this is like a covariance matrix? Okay, so generally this is giving your variance and this is like covariance. So this is giving you the relation between two variables and each cell will have some value, and using these values we can compute the final result, whether they are dependent or independent. We just put them in a, and this table is sometimes called, generally referred to as contingency table. Generally contingency table means like dependency table. So we try to find out whether they are dependent or not. So this table, when we put this data, that is called contingency table, okay. And the test statistic here is a bit modified format of the chi-square only. There we had only single variable and now we are having two variables together because one was known, other was unknown here, and here we have both are unknown. So we'll take both of them into account, and then test statistics becomes x square calculated is equal to summation over both row and column. So I equal to 1 to r and j is equal to 1 to column value, and then same thing. This will be the OIJ and EIJ for each I and j. So I will be moving from 0 to r, and then j will be moving from 0 to c. So each cell will have values like this here, OIJ, EIJ. Okay, we'll see how to compute that. So it will just compute the OIJ minus EIJ whole square by EIJ. So it's the same thing, it is just across this complete table that we got x and y. We put them together and then we are trying to find it. So we are trying to do a test of independence. So now let's revise our basic probability. If two random variables, if they are independent, then what can we say? If A and B are independent, what do we say? That P A and B is equal to P and A into B. This is also written as P A like this, P A B, or joint probability is equal to the product of individual marginal probabilities. So simply put, the A and B is P A and P B because they are independent. This is your simple test of the formula for independence. Okay. So now let's do the test. Okay. So what is a null hypothesis? So we'll put it in the terms of hypothesis testing. So null hypothesis is that variable A and B here or whatever are independent. So there is no change or nothing, no impact of each other. So that's your default null hypothesis. And H alternate is that variable A and B are dependent. If the null hypothesis does not hold, or if it is rejected, only then we will come that no, they are dependent. Okay, and then let's define all the variables. R is equal to number of rows, C is equal to number of columns. Okay, in this table that we have put all the values so that we can compare. I'll give you an example after this that will make it very clear. And now let's calculate all these P probabilities so that we can compute. So probability of A of I is equal to, what will be? For this ith, so all these are categories. So I0 to R, this is like category. I'll put it as 1, okay, for simplicity, because these are categories. So each row will have one category and each column will have one category. So these are two different variables. So for example, okay, so this is gender, male, female, two categories, and this is the type of drink. I'll give you an example also, whether they drink tea, coffee, or soup, or just milk, something like that. So I can have different categories on this. So I have one category as tea, one as coffee, one as milk, one as soup, one as juice. So these can be different categories. Is there any relation between these categories and the gender, male and female? Like if male, female, certain categories, and female prefer certain categories, is there some relation? Are they dependent or are these independent? So that's what we'll try to figure out from this test. Okay. So these are the categories. Each column is a different category. Each row is a different category. So probability of AI, probability of the ith category for A, this is A and this is B. So instead of X and Y, I'll write the consistent notation. This is A and this is B. Say on the row I have A and on the column I have B. Let me highlight this so we don't confuse. Let me use another color so that it is not lost. We'll come back and refer again. So what will be my probability of ith category, and say my total number of samples I have is n. So n here, n is equal to total number of samples. So probability of AI will be row total of the ith category by n, okay, where n is the sample size. This is the total number of samples. Similarly, probability of BI will be column total of the ith category by n. Now, what will be the expected value? Eij is equal to the cell value for this expected value here, any ij, this is I, this is j. So I expect them to be the product of these two. So this will be equal to, and expected ij for all the cells will be n into probability of AI into probability of bj, because there will be n cells, right? R into C, there will be n cells. Okay, how do we reach to this formula? Okay, expected value. So this will be here. So now let's do this. So n is here, okay, and then row total I into by n into column total I by n. This is the expected value for ij. So this n and this n cancels out. So finally my Eij will be row total of ith, and this will be j, sorry, this will be j, this will be j, okay, and j I'm using to measure count here the columns. Row total I, column total of j by n, because only one n remains here, okay, and my Oij is the, so these are the all the variables I'll declare only, and Oij is the observed count that I'll get from the data itself. That is the observed count of ith category. Okay, so I have defined all the required variables, Oij, Eij, that is the main thing, and R and C for what is my test statistic. So this is my test statistic here, and plus I have degrees of freedom is equal to, this is equal to again, sorry, this is equal to r minus 1 into c minus 1, because we have found out that only n minus 1 variables can vary independently. The nth variable is dependent on other n minus 1 variable. So my degrees of freedom which can change independently are n minus 1. So r minus 1 for the rows and c minus 1 for the columns. And so this will be my degrees of freedom. So now I have all the data, because this will be used, this degree of freedom will be used to see the chi-square table. And this will give me the test statistic value. And what is my null hypothesis? That variable are independent, and the alternate hypothesis is that this is dependent. So now based on all this information, let's solve a small problem and this will set everything clear. So let's do a question quickly. So the question is, we survey, again whatever example I'll just carry the survey, n is equal to 100 students. I'm surveying 100 students to find out what is their preferred beverage, and I'm categorizing them on the basis of their gender, male and female. So I'm surveying 100 students, and I'm finding their beverage preference. What is their preferred beverage, tea or coffee? And the categories are male and female. Okay. So I'll create the contingency or the dependency table. So I have gender on one side. Okay. And this will be, okay, let me put it. So we have sorry, tea here, coffee here, and we have male here, female here, like this. Okay, and we have the numbers. Okay, say for example, these are the this is my on the A side, and this is my B variable. Okay, this is a variable, this is a B variable. So I have to find out whether these two variables are dependent or not using my chi-square test of independence. So let me put where these are the observed values. This is the data that you have been given. Okay. So what is the variable? That 20 out of 100, 20 like this, 10 like this, 30 like here, and 70. No, 70. No, 70 is the total. 40. So I'll just draw one more line here and one more line here. So what is the total number of males? 50. Total number of females? 50. Total number of people who like tea only? This is 30, and total number of people who like coffee, this is 70. So total number of males is this. This is a AI. This is a A1. So if you write the cell, this is 1, 2, 1, 2. So this will be 1, 1. This will be 1, 2. This will be 2, 1. This will be 2, 2. Okay. So all the values, this is observed. Similarly, we'll compute the EIJ also. These are the observed values. O11, O12. So this is the I. I is varying from 1 to 2, and J is varying from 1 to 2 here, this side. This is your data. Now let's put that into the statistic. So what will be the, first of all, degrees of freedom? This will be equal to R minus 1 into C minus 1. So this will be 2 minus 1 into 2 minus 1. This is equal to 1. 1 and 2, 1. And what will be my chi-square for 1? This will be the formula sigma I equal to 1 to 2, sigma I equal to 1 to 2 for rows and columns. Then OIJ minus EIJ whole square by EIJ. Okay. So let's set this up, and then what is my null hypothesis? That nothing is changed. The gender preference are independent. Okay. So this is a hypothesis test. So my null hypothesis is that gender and beverage preference are independent. And what is my alternate hypothesis? No, gender and beverage preference are dependent. So all the tests will be performed on the null hypothesis itself, and everything, all the observations will be made based on the null hypothesis. So let's calculate them. So all the OIJs I have, OIJs are, these are the observations. Now we have to calculate the EIJs. So E11, E12, E13, E11, E12, E21 and E22 needs to be calculated. So what is your EIJ formula? So this is your row total ith into column total jth by n, total number of this. So let's do E11 is equal to row total of 1. So I'm doing of 1 and column total of 1. So first row total of 1. What is row total of 1? So this is a row total of 1. So this is 1 from A side. This is your A and this is your B, I and J. So 20 plus 30, this is 50. So row total of I is 50. And the column total for I, that is first one is T. This is this side. This is 30. And this is into by 100. Similarly, E12, so A is 1 and B is 2. So this one. So A will remain 50 itself because this is coming from here, and this is 2. So 2 is 70. This is for coffee. This is your second category from B side. So first category from A side, which is male, and second category from B side, which is coffee. So this is your E12, which is 50 into 70 by 100. Now E21 is equal to, now second category from A side, that is female, and the first category from T side. So what is the sum of this? This is 50 again. This is the row total of this second I is equal to 2, and the sum total of T, or the first column, is 30 again. This we know. So now we remember all this. So this is 50 into 30 by 100, and similarly E22 will be equal to 50 into 70 by 100, because again this will remain 50 and this sum for coffee will be 70 only. Okay, let's do quick calculations. 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So this is 5 3s are 15, this is 5 7s are 35, this is 5 3s are 15, and this is 5 7s are 35. And now let's put all these value in my chi-square calculated. This is equal to sigma I equal to 1 to 2. So we'll just put all these values together. Okay, no, sigma I equal to 1 to 2, sigma I equal to 1 to 2, and then let me write the formula so that we don't forget it. Okay, so this is two categories are there. So E11, E12. So OIJ for first one is 20. This is the observed value, 20. I'll just put 20 minus 15 E11 whole square by expected value 15. Similarly, E12, this will be 30. Sorry, 30 here. This is the observed value. O12. I'll write the values, then you can find out. This will be 30 minus 35 whole square by 35 plus 10 minus 15 whole square by 15 plus last one is 40 minus 35 whole square by 35. This is the expected value, right? 20 minus 5, all is 5 differences there, right? 20 minus 5, 30 minus 5, 10 minus 5, 50 minus 5. So all is 5. So this is 25 by 15 plus 25 by 35 plus 25 by 15 plus 25 by 35. Do the calculation, and this will finally come out to be equal to 4.76. Okay, degrees of freedom we have calculated. So DOF is equal to 1. So now let's see the critical value. Now let's set this. So we have null hypothesis that gender are independent, and alternate is that they are dependent. We have calculated the test statistic. We have the value now. We use the chi-square test of independence. That was our choice of test. This is a test statistic value. Now let's set up the alpha, that is 5% only, that is 0.05. This is the next step, and then let's calculate the p-value, or let's p-value for this. P-value we have this. Okay, here Let's find out the critical value for alpha. So we'll find out the critical value so that we can find out critical value at P alpha. So this is for 5% and degrees of freedom 1. So we need to find chi-square for 0.05 and degrees of freedom 1. I think we had the same value last test also. So let's check. Yeah, same value. So I'll just show you same thing. So we have this, right? So let's come back. So we had the same alpha last time also, and the degrees of freedom was same in this also. So we'll again get the same value, 3.84. Okay, let's come down. So the T critical value for against this will be 3.841. Okay, and now since, so we'll plot it. Let me show you again so that you get used to it. So where is my critical value? This is your 3.84, means the area under the curve. This is your 5%. This is equal to your alpha significance level. Okay, and what is my P value? The T observed. The P value I cannot get it from. I can plot this 4.76. So 3.84. So 4.76 will be somewhere here. So definitely this area is less than, okay, this is less than 5%. So it is less than the significance level. So if it would have been greater than 5%, say 7% or 10%, then we would have accepted this. But this is less than the significance level, means this is not so significant. Whatever we have, whatever data we have got, this is not statistically significant. So based on this, finally we will reject the null hypothesis, that, and then we will accept the alternate hypothesis, that gender and beverage preferences are not independent, but they are dependent. So from chi-square test of independence, we found out that both are dependent. I hope this is clear now.